In this video, we want to talk about some of the properties about functions. And more specifically, we'll first talk about looking at the graph of a function, finding out when it has symmetry with respect to the x-axis, y-axis, and origin. And then we'll take a look at when a function can be considered even, odd, or when it's not either one of these two things, so neither. So let's first start off with that idea of symmetry. The good news is that even though we're going to be talking about functions, that the idea of something being symmetric is really the same idea that you learned long ago, probably way back in elementary school. And that idea is that if you have some sort of object and you're trying to see if it's symmetric, that you're basically looking for some imaginary line on that object such that when you fold it on that line, it matches up with itself. Okay, so below I have an example of one of these objects, and it's basically a star. So imagine maybe folding this star straight up and down. Now, if you fold it along this blue line, you'll see that the star matches up with itself. So we could say that this star has symmetry and that blue line would be the line of symmetry. Now, of course, some objects are very special, like this star, and that might not be the only place where you could fold it. For example, say I chose this place, the diagonal, so from the lower point up to the corner. If I fold it along this line, it also matches up. So this is another example of symmetry on the same object. Now, the star is a very special object. I have lots of lines of symmetry for this particular thing. Now, we're going to use the same idea of symmetry, only instead we'll be looking at the graphs of different functions. So using this idea of symmetry, let's see if we can take a look at a graph and basically determine if it has symmetry. So if you look at this graph that I have below, imagine that there's some sort of place that we can fold it and that it would line up with itself. If you look at the graph for just a little bit, you can see that if you fold along the y-axis, that this graph would sure enough match up with itself. Well, when one of these lines of symmetry lines up with an axis, this is what we are really interested in. So below, that line of symmetry is right on the y-axis, and I would say that this graph has symmetry with respect to the y-axis. Okay, so it's really the same idea, only we're especially interested when the symmetry lines are on an axis. So let's give this another try, maybe with a different graph. So go ahead and look at this one for a bit, and again ask yourself, does this have symmetry? And it shouldn't take too long, and you'll notice that yes, it does have symmetry. This one, if you fold it along the x-axis, it will match up with itself. So we can say that this graph has symmetry with respect to the x-axis. Now, again, I want to really emphasize that we're only interested when the lines of symmetry end up on one of these axes. Lots of graphs could have a line of symmetry that just lines up some other place. And with those, we're not quite as interested in them. Only when they line up on one of the axes. So that basically takes care of when something is symmetric with respect to the y-axis and when it's symmetric with respect to the x-axis, which leaves us with only one more to talk about. When is something symmetric with respect to the origin? Well, to really visualize something like this, you want to think of folding it twice, once over the x-axis and then once over the y-axis. So let me show you what I'm talking about with this example. Here I have a graph, and I claim that it's actually symmetric with respect to the origin. And here's how you can visualize that, all right? So let me chop off part of the graph, and maybe just look at the part in the first quadrant. I'm going to take that part in the first quadrant and first fold it over the x-axis. Okay, so that will give me a new part down in the blue. Now imagine taking that blue part and folding it one more time over the y-axis. This will give us the green portion. Now that green portion should line up with the original graph. So let's go ahead and remove all that I have here and see that sure enough the green part matches up with the original function. And since it matches up like that, that's how I know that this has symmetry with respect to the origin. Now another way that you can kind of visualize this is that you're basically taking the graph and you're rotating it 180 degrees. As long as it does that rotation and then matches up on itself, that's how you know it has symmetry with respect to the origin. Now hopefully after seeing a few of those examples you have a much better idea of what it means to be symmetric when we start talking about graphs. Here's the thing though, oftentimes when we have a function or some sort of equation, we don't always know what the graph of it looks like. Well, we're not necessarily out of luck. You can still test whether something is symmetric with respect to the x-axis, y-axis, or origin using just the equation, so you don't even have to know what it looks like. And these are basically tests that you do to the equation itself. So in order to test if something is symmetric with respect to the x-axis, we want to replace the y with a negative y and then see if it produces an equivalent equation. Now that seems kind of backwards, doesn't it? We're testing for x-axis symmetry and we're replacing a y with negative y. Just, hold on for a little bit. I'll show you with a few later examples why this really isn't backwards and that we're doing what we need to do. Now with y-axis symmetry, in order to test that, you can replace x with negative x and then see if it produces an equivalent equation. And lastly, if you want to test if something is symmetric with respect to the origin, you replace both x and y with negative x and negative y, and then see if it produces an equivalent equation. Now that we have a test for symmetry when we don't have the graph, let's go ahead and give it a try with this example here. So I have the equation x equals y squared plus 2, and I'm really curious to see if this has symmetry or not. And I'm not going to look at the graph. I'm basically going to use those tests from the previous slide to see if it has symmetry or not. So first I'm going to test if it has x-axis symmetry. That means I need to take the y and replace it with a negative y. Okay, so I'm basically just going to substitute that right in there. Now my goal is to then start taking this and try and simplify it to see if it produces the same equation that I started with in the very beginning. Okay, so let's work with this for just a little bit. If I square a negative y, that's really the same as saying negative 1 is being squared and y is being squared. So I'm basically splitting up that square over the negative sign and over the y part. Now the reason why I'm doing that is when you square a negative 1, you get just a single 1. And of course 1 times anything is anything. So that guy just gets removed entirely. Now if you look at what it's simplified to, x equals y squared plus 2, that's exactly what we started with at the very beginning. So in summary, we took y, we replaced it with negative y, and we have an equivalent equation when we're done. Well, that's exactly what the definition says about x-axis symmetry. So without even looking at the graph, I know that this has x-axis symmetry. Alright, just for fun, let's go ahead and run the second test to see if it has y-axis symmetry. Alright? So again, taking x equals y squared plus 2, I'm first going to replace x with a negative x. And my goal is to see if this simplifies in some sort of way such that I get back to my equivalent equation. Well, if you look at this one, no matter how you try and simplify it, it's not going to be the same as what we started with. Well, that means this one basically fails the test. This equation does not have symmetry with respect to the y-axis. So, you can basically see how these tests work. You start replacing the variables, simplify them, see what you get, and see if it's the same as the original. Alright, now that you know a little bit more about the test, let's see visually exactly why they work. Why is it when you're testing for y-axis symmetry, you actually start replacing x's? Well, let's see what's going on here. So remember this graph before? Before we agreed that this has y-axis symmetry. So in order to see why it matches with the test, let's start taking an arbitrary point on that graph. Okay, so I'm going to pick the point, let's do the one up in the corner, at 6, 9. Now, if this is symmetric with respect to the y-axis, it means it has a twin point just on the other side, located at negative 6, 9. Now, notice something very special about those 2 points. It's like we've replaced the x with the same value of x, it's just negative, and we're getting the same y values. Well, that's exactly what we're doing when we're testing. We're replacing x with negative x and seeing if we get an equivalent equation. So visually, the same thing is going on. Well, let's do it for one of our other tests. Let's do it for this one. This one has symmetry with respect to the x-axis. So let's go ahead and take an arbitrary point on here, 4, -8. Since it has that symmetry, it has a twin point on the other side at 4, +8. Again, notice what's going on here. The x values are the same, but the y values are just different by a negative sign. And that matches up with the test. When you test for x-axis symmetry, you replace a y with a negative y to see if you get an equivalent equation. All right, well that really leaves us with only one more test to visually compare, and that's when something is symmetric with respect to the origin. So let's again grab some sort of arbitrary point on the line. So I'm going to pick the point 2, 5. Now if this has the proper symmetry, where do you think that twin point is? If you said -2, -5, then you're right. And sure enough, that matches up with the test as well. Because when we're testing for symmetry around the origin, we replace x with -x, and we replace y with -y, then see if we have an equivalent equation. Alright, so that is a lot of information just on symmetry. And it seems like we haven't even touched on when a function is even, odd, or neither. But actually we have. You see, those terms, even and odd, are actually just special terms given to functions when they have certain types of symmetry. In fact, you can call a function even if it is symmetric with respect to the y-axis. You know, those are really just two synonymous things. You know, call a function even or call it symmetric with respect to the y-axis, same thing. In a similar fashion, you can call a function odd if it is symmetric with respect to the origin. So remember that taking a graph and rotating it 180 degrees, you know, if you get a graph like that, you can also call it an odd function. Now, you might be wondering, hey, wait a minute. What happens if I have, you know, an equation that is symmetric with respect to the x-axis? Does it get a special name? Well, the short answer is no. You see, if you have a graph that is symmetric with respect to the x-axis, then it actually fails the vertical line test, and it's not even a function. And since it's not a function, we're not going to be too worried about those, and so it does not get a special name. And so you can see that will give you even and odd functions, and if it doesn't fall under one of those two categories, you can just say that it is neither.